Now that we understand the asynchronous serial protocol, how do we implement it? Well, one way is simply to use parallel I/O pins to implement the transmit and receive channels. This code shows how to do a software-driven serial I/O implementation. This works, but it's not an efficient use of CPU resources. A serial protocol implemented by software and parallel I/O pins is called bit banging. This code uses lat-B2 as the serial transmission line and RB3 as the receive line. We're going to use this macro STX to stand for lat-B2. This subroutine here, outchar soft, is going to send 1 byte of data in asynchronous serial protocol format using 1 start bit, 8 data, and 1 stop bit. Coming into this subroutine, we're going to assume that the transmit line is high. So the first bit that we need to send is the start bit, which is always a 0. So we're going to set the transmit line to a 0 and then delay for 1 bit delay. This subroutine is implements a software delay based on our chosen baud rate. Once the start bit is sent, we then need to send the 8 data bits. So we're going to have a loop that's going to loop 8 times, sending each data bit. In this if test right here, what we're going to assume is we're going to assume that the bit to be sent is in the least significant bit. Recall that this protocol sends data least significant bit to most significant bit. So this logical AND is going to test the value of the least significant bit. If it's true, then this code right here is going to be executed, and we're going to set the transmit line to a 1. If it's a 0, then the else clause is executed, and so we'll set the transmit line to a 0. At that point, we'll do 1 bit delay, and then we'll take our character and shift it to the right by 1 to move the next bit that we need to send into the least significant bit. Once all 8 bits are sent, the only bit left to send is going to be the stop bit. So we're going to set the transmit line to a 1. Recall that the stop bit's always a 1, and do 1 final bit delay before exiting this subroutine. This subroutine here is going to be used to receive 8 bits of serial data. We're going to use a temporary variable C here to hold our data, and what this subroutine is going to initially do is going to initially wait for a high to low transition on our receive line. So this while loop says that while this is a 1, simply wait until it becomes a 0. Once it becomes a 0, we know that we have the start of the start bit. So then what we're going to do is we're going to delay for 1/2 bit time. That's going to put us in the middle of the start bit, and at that point we can now start receiving our bits. We're now going to enter a loop that's going to loop 8 times to receive all 8 bits. The first thing that we're going to do in this loop is we're going to do a full bit delay. That's going to put us into the middle of the next bit. Once we've waited a full bit delay, we're then going to test the value of the receive line. Notice that this variable was initialized to 0. So what we're checking the receive line for is if it's a 1. If it's a 1, then we need to modify some bit in our temporary variable. And what we're going to do is we're going to set the most significant bit. Now we're receiving bits least significant bit to most significant bit. So why are we setting the most significant bit? We're setting the most significant bit because then what we're going to do in the next step is we're going to shift this to the right. So we're going to move this bit towards the least significant bit. We're only going to do this shift if our count value is not equal to 7, because if it is equal to 7, then we've just received the last bit, which is the most significant bit, and we've set it to a 1. So we do this 8 times, get all 8 serial bits. We're going to store them into this temporary variable C. At that point, the only bit we have left is going to be the stop bit. So we're simply going to wait for 1 bit delay. We're not going to sample the line. We're simply going to assume that the stop bit has been sent correctly as a 1. And then we're going to return the serial character that we've just read. So while these subroutines work, they are not an efficient use of CPU resources. The main problem with these implementations is that the CPU, when it's executing this subroutine, outputting a character, or this subroutine when it's inputting a character, it's not doing anything else except doing that. It's also, serial I/O is slow. We're spending 99% of our time in these delay functions. So is there a better way to do this? And the answer is yes, which we'll see in the next slide. So the software routines in the previous slide could have been written in a more efficient manner using interrupt-driven I/O, But the absolute best way to implement the serial I/O is to have a dedicated hardware module to do that. And really all modern microcontrollers, when they implement serial I/O, use hardware modules to implement the serial I/O. On the PIC-24, this is called a UART, which stands for Universal Asynchronous Receiver Transmitter, and is simply a hardware module that's going to implement both transmit and receive of serial data. This frees the processor from having to implement these functions in software, so the PIC-24 can be doing other things while the hardware module is either transmitting data out or receiving data in. The particular PIC-24 referenced by the book only has one UART module referred to as UART1, but other family members can have multiple UART modules on the same chip. As with the timer module, you use special function registers to interact with the UART. The RX register holds receives characters. You read this to get a character. To send the character out the serial port, you write that character to the TX register. The status and mode registers contain configuration bits and status bits for the module, while the B or G register is used to set the baud rate for the serial port. Our library hides the details of these special function registers behind macros and library routines. This slide shows a diagram of the transmitter hardware within the UART module. The purpose of the UART transmitter is to shift serial bits out of the TX bin. It's going to do that using an internal register called the transmit shift register. In order to get data into the transmit shift register, what we're going to do is going to write a byte to the transmit register. The transmit register is actually a 4-element FIFO. Let's assume that this transmitter is totally empty. Then when you write a byte to the transmitter register, what's going to happen is in the next clock cycle, that byte is going to be transferred to the transmit shift register, and then the transmitter is going to begin shifting bits out of this pin. While the PIC-24 transmitter is shifting bits out of this pin, the PIC-24 code is free to write new values to the transmit register. Because the transmit register is actually a 4-element FIFO, it could actually write 4 bytes to this register before the FIFO fills up. So this transmitter can actually hold 5 bytes of data. 1 byte in the transmit shift register is currently being transmitted out, and 4 bytes being held in this transmit FIFO. Before writing a byte to the transmit register, you have to check a bit called the transmit buffer full bit to make sure that there is actually space in this FIFO. If this bit is equal to a 1, it means that the buffer is full, and you have to wait until this bit becomes a 0, indicating that it's a free spot in the FIFO. If it's a free spot in the FIFO, then you can write your byte to the transmit register, and the PIC-24 can go off and do other things while that byte is being transmitted out the transmit pin. So this code here shows our outcar1 routine that is used to actually send data out the UART. It's going to take in a byte, and it's going to, first thing it's going to do is going to use this macro called isTransmitBufferFull UART1 to check to see is the FIFO has an empty spot. And all it's doing is just checking this TX buffer full bit to see if it's a 1 or not. If it's a 0, then we exit this while loop, and that will indicate that there's a free spot in the FIFO, and then this code simply copies this character to the TX register of the UART. In your code, you've been using the outcar routine to output a single character. What this is doing is simply saying there's an internal variable that sets the default UART, and the default UART for our particular PIC-24 is going to be UART1, so it's going to end up calling the outcar1 function. If there were multiple UARTs on the PIC-24, then you could use these functions here, outcar2, outcar3, outcar4, to write characters to the other UARTs. This slide shows a block diagram of the receive hardware in the UART module. The job of the receive hardware is to accept serial data on the RX pin and deliver it to the PIC-24. It does this by shifting serial data into an internal shift register. Once all bits of a frame have been shifted in, this data is transferred to a 4-element FIFO. You get data out of this FIFO by reading the RX register. This flag right here, the RX interrupt flag, will be set to a 1 if data is ready to be read from the RX FIFO. For each byte in the RX register FIFO, there are two accompanying status bits that indicate two different errors that can occur on a particular byte. One of the errors is called parity error, P-E-R-R, and if it's set to a 1, then it indicates that a parity error was detected for this byte. If the particular data protocol you're using have it configured for it does not have parity, then this bit is always going to be a 0. The other error that can occur for a particular byte is called a framing error, F-E-R-R, and what this is, if this is a 1, then it indicates that the receive shift register detected the stop bit as a 0 instead of a 1. Recall that for a stop bit, that should always be equal to a 1. If you read, if the receive shift register sees a 0 for a stop bit, then it means that this is some kind of transmission error has occurred, and it generally occurs when there's a mismatch in baud rate between sender and receiver. Note that between the four bytes in the FIFO and the 1 byte in the shift register, this can store a total of 5 bytes. What happens if I get another byte in on the receive pin whenever the FIFO and the shift register is full? If that happens, it's going to generate what is called an overrun error. An overrun error is a global flag for the receiver hardware, and when that happens, the receiver hardware will shut down and will not receive any more characters. Their overrun will be generated when I get the start bit of this 6th character coming in. You must guarantee your PIC24 code must read the UART receiver often enough to prevent overrun. So to summarize the receiver error conditions, there are 2 bits that are stored for each byte received, framing error and parity error. Framing error is where a stop bit is read as a 0 instead of a 1. Parity error is when the wrong parity is received for a byte. There is also a global error bit that is set for the receiver hardware overrun error that is generated if the start bit of the 6th character is received when the FIFO and the receive shift register are both full. The ncar1 function is the function we use to read a character from UART1. It waits for a character to be available by using this macro, is car ready UART1, to check for data availability. This macro is using the RX data available bit within the UART1 module to see if data is ready. This bit's going to be set to a 1 if if at least 1 byte is ready to be read. Once data is ready, we call a function called check RX error UART1, which is going to check the byte for parity error, framing error, or overrun error. If any one of these errors occur, then we're going to call our internal function report error with an informative string that will generate a software reset. If no error occurs, then we're simply going to return the value in the U1 RX register. The in-car routine is like the out-car routine in that it uses this internal variable to determine to read a character from the default UART. In this case, where our particular PIC24 used in the book, it's always going to be UART1, so we'll always be calling the ncar1 function. If you want to read data from other UARTs, you can use these functions here if your PIC24 has multiple UARTs. The BRG special function register is used for baud rate generation. It acts as a period register in the same way as the PR2 period register function in the timer 2 module. This formula right here computes baud rate from a given BRG value, a given instruction cycle clock frequency, and this S parameter, which is either 16 or 4. This 16 means that 16 clocks are used to output a bit or to sample an incoming bit versus 4 clocks. In our code, we always use the 16 mode. Typically, you know your baud rate and you want to compute the BRG value needed to get to that baud rate. So solving for BRG, we get BRG is equal to the instruction cycle frequency divided by S times the baud rate -1. This calculation can be done at runtime, and we do that using this function right here, config baud rate UART1, in which we pass in a baud rate and we calculate the needed B or G value. This is a simplified version of the function. The actual function in the library does error detection to see if this value right here is greater than 65,535, which would indicate that your baud rate is out of range for the other given parameters. This table shows some standard baud rates and the B or G values necessary to achieve those baud rates for our standard clock frequency of 80 megahertz. Because these baud rates are not evenly divisible into this clock frequency, the actual baud rate we achieve is somewhat different from this baud rate, and this is the percent error. Recall that we need practically about 3 to 4% matching between receiver and transmitter clocks for two different receivers and transmitters, and so these percent errors down here are okay. This is getting fairly large. Recall that the internal fast RC oscillator, because it uses resistor capacitors for oscillation along with inverters, it means that its clock frequency can be as off by as much as 2 to 3%. That's going to add to this percent error. If you want a more accurate clock, then you can use an external crystal. This particular frequency, 7.3728 megahertz, has the feature that the standard baud rates are exactly divisible into it. If you use the internal PLL to boost this clock frequency by 10, then you can get an internal clock frequency of 73.7 megahertz, which is pretty close to 80 megahertz. And now the B or G values that you calculate will give you baud rates that are exactly equal to these standard baud rates. To wrap up this video, we'll take a very brief look at the config UART1 function, which accepts as parameter a value for baud rate. This parameter is passed to the config baud rate UART1 function, which is going to use this parameter to compute the needed B or G special function register value. Before we do that, we configure two pins to serve as RX and TX. It turns out that the RX and TX pins on the internal UART1 module are not assigned to any external pins on our particular PIC24, so we have to map them to remappable pins, and we chose these two pins for the RX and TX functions. We then going to configure a data format for UART1, and in our examples we always use 8 data bits plus 1 stop bit. And the last function is called enable UART, which simply turns on the UART and enables both receiver and transmitter hardware. So in our previous examples and lab experiments, we have seen that we use a serial port in a PIC24 for several functions. We use this to connect to a personal computer, and we use a bootloader program to download programs from a personal computer into the PIC24. We also use this port for debug messages and user I/O from our programs. So the question is, how does this physical connection between the PIC24 microcontroller and a personal computer actually work? Well, there are two ways that this can be connected. An older method was that personal computers used to support a physical interface standard called RS-232. This meant that they had a special connector in the back that's called a DB9, and this supported a standard named RS-232. This standard has logic levels at voltage levels that are not compatible with CMOS voltage levels. CMOS voltage levels, or logic 0 is 0 volts, while logic 1 is whatever VDD is. In our case, it's 3.3 volts. For RS-232, however, logic 0 is plus 3 volts to plus 25 volts, while logic 1 is minus 3 volts to minus 25 volts. Notice that there's a logic conversion here. This is positive voltage for logic 1, while this is negative voltage for logic 1. So in order for these two devices to talk to each other, you need a special interface chip to convert between these two logic levels. These days, most personal computers no longer have the special connector in the back that supports RS-232 because this serial standard has been replaced by the Universal Serial Bus standard, which is standard on all PCs. So now what we do is we use a special cable, and these are manufactured by several manufacturers. We use this particular one that converts between the Universal Serial Bus protocol to the asynchronous serial protocol. This particular cable brings out a 6-pin header. On the 6th pin we have ground, receive, and transmit, as well as 5 volts from the universal serial bus cable. You could actually use this to power your PIC24 board, but we don't do that because we don't want you damaging your port if you draw too much current from it. It also has an extra control line on it. This line is called request to send. It's actually part of the RS-232 standard, and you can remotely toggle this line up and down, and Bully Bootloader uses this line to remotely toggle M-Clear on the PIC24 microcontroller. Conversion from the USB, the universal serial port bus, to asynchronous serial is not trivial. The USB protocol is very complex. The asynchronous protocol is not as complex, and that requires some processing power. And it turns out that there's a processor chip hidden in the connector here that does all of this work. I want to point out that this particular cable, the voltage levels on these pins are 3.3 volts, so they're directly compatible with the VDD that we use for our PIC24 microcontroller. So we need no special chip to convert the voltages from this to this. They're compatible.